Hello everyone, welcome to Digital Media E10. This is week 9, digital cameras continued. Of course, at the very beginning of lectures, we'll continue with our habit of some brief announcements. Problem set 4 is due tonight, project 4 is due next Wednesday, and problem set 5 was released today. Now normally, for all of the prior problem sets and projects, we've been asking you to take about 2 weeks to complete them. But in this case, problem set 5 actually has a due date that's 3 weeks from today, which is different than originally scheduled. Now the reason for this is that, as you might recall from last week's set of announcements, we swapped some of the lectures. I realized that the color and artifacts lecture actually contains some material that is actually covered by problem set 5. So we're giving you an extra week to make sure that you're actually able to attend or watch that lecture before completing the problem set. Now that does mean that the due date for problem set 5 also corresponds to the final project proposal due date, which also is that same day, I believe. But this hopefully is not going to be too much of a problem, since you're now just getting extra time to do this problem set and not any less time to do any other assignment. So do be sure that you take a look at that. A lot of the material will be covered today, in the past few weeks as well, and also in the color and artifacts lecture. And this marks the end of the problem sets. This will be the final problem set for this semester. And after this, there will just be essentially the final project. Once project 4 is in, once problem set 4 is in, once problem set 5 is in, it will only really be the final project for the duration of the semester. And the specifications for that will be released next week, but just a quick preview, we're essentially going to ask you to make one. What that basically means is that you will have to think of some sort of photographic related project. Some people in the past have done a wide variety of things, including making a web page. Some people have wanted to create a series of photographs that are meant to just be like an exhibition of photographs, for instance. Some people have actually taken the time to make historical articles about their town or about their locale and actually document some of the history of that using photographs. The main point of the project will be revolving around photographs, but you are really freely available to do any number of things that you may want. And more details on that will be forthcoming when we actually release the final project spec. But just start thinking now about what sort of thing you might want to do, what sort of thing you might want to accomplish with your final project. A number of people in the past have also enjoyed taking one of their prior projects, projects 1 through 2, 3, or 4, and actually expanding on that a great deal to complete their final project. And again, we'll talk more about that in the coming weeks. Now last week, we started talking a bit about digital cameras, and specifically we talked at length about digital cameras, their sensors, and the various sensor sizes that exist for these digital cameras. And nowadays what we find, in recent years especially, is that we have a lot more compact cameras that are actually increasing the size of their sensors, which is great overall, because that means that pixel sizes tend to increase a bit, and there's a number of advantages to that. But also it sort of decreases this variability in the number of different sensor sizes that we have, which is useful when talking about the focal length equivalent, comparing it to a 35mm lens. And this slide in particular was used to sort of demonstrate the image circle projected by a lens onto the camera behind it. So lenses are of course circular, and so the image that they project is circular, but the sensor that we have is rectangular. So we don't actually see a circular image necessarily. What we see is a square or rectangular image because of the size of the sensor. Now you can actually observe the circular aspect of a lens if you take a lens that is meant for a smaller sensor size and put it on top of your camera that has a much larger sensor. So for example, Canon and Nikon have digital lenses or EFS lenses that have an image circle for the crop sensors, for these smaller sensors. And so they project an image circle that is in fact smaller. And if you were to just hold that in front of your full frame camera, it's not necessarily, I don't recommend trying to shoehorn it on, because there is a reason that these lenses are designed not to actually be placed onto their larger sensored cousins. But if you were able to take a photograph with that, you would actually see that the corners of that image were cropped. There's a significant amount of vignetting because of the smaller sensor or the smaller lens size as a result. But the main takeaway from this slide was that if we are to compare against full frame sensors, which is very common, the thing to do in digital cameras, which full frame, by the way, in this example is the red rectangle, we might have an APS-C size sensor, which has a crop factor of about 1.6. That is the size of the blue rectangle. And what this results in is different fields of views for the same lens. For the same actual physical focal length, we actually see different fields of views. And what the way that this manifests itself is that the cropped sensors are just that. They are, in fact, cropped versions, which means that we have to actually decrease the size of the focal length or decrease the focal length of the lens if we want to try to capture the same field of view for that particular camera. Now, I did just want to talk a little bit more about this, or at least rehash the same idea from last week, where we were talking about how the sensor size can actually affect the depth of field. And what this really means is that that's not truly an accurate thing to say. It's not really the size of the sensor that does this, but the results of that. And what I mean by that is this exact discussion that we had just finished a moment ago of requiring lenses to have smaller focal lengths to capture the same fields of view also means that the other components in the lens tend to decrease as well. So if we were to actually maintain the same f ratio, the same f number, from this lens, this original lens to this smaller lens that has the smaller focal length, what this means is that we've in fact changed the size of the aperture, the actual physical length, rather diameter, of the aperture within that lens. And it's really this in combination with a criterion for resolution. In this case, we are expanding the size of these images to the exact same size, so that factor sort of goes away. That dictates ultimately what depth of field we are going to have within our image. And of course, by SLRs and larger sensor cameras having the capability to actually stop down the f number, and by that I mean make the aperture smaller or increase the f number significantly, this means that these larger cameras tend to have a superset of all of the capabilities of the small cameras. So whereas a small camera, you might, and by small camera I mean a camera with a smaller sensor than some other camera. So by a small sensored camera that might actually appear as though it has a very large depth of field, you can in fact replicate this with your larger camera as well. So it's not that there is an inherent feature necessarily to this smaller camera, it's just that it's the nature of the smaller aperture, and you can of course replicate this with the large camera. So this really sort of alludes to this compromise that we've been alluding to or talking about for weeks now. Every aspect in photography is a compromise. If we were to continue taking photographs with a larger camera, then we get this capability of having the nice background blur, or the capability to increase the depth of field and actually get more in focus, but at the expense of actual cost and perhaps the size of the camera as well. So take all of these considerations in mind when you're actually looking at a camera system or looking to change your camera system or modify your own workflow. Now, we also talked a little bit about the distinction between what ISO actually is versus how we described it early on. So you might recall very early on we had described ISO as quote-unquote sensitivity, but saying that this isn't really necessarily an accurate way of describing what is happening in the sensor when we're increasing the ISO. But it is a good proxy for it in terms of exposure. If you want to think of increasing the actual sensitivity of the sensor because it makes it easier to think through manipulating the exposure values, then it's fine, but realize that it's not accurate to actually say that we are changing the sensitivity of the sensor. In fact, what we are essentially doing is allowing the wells of the individual pixels to fill up a smaller amount and actually multiply that to represent the full values that we had before. It's essentially changing the amplification of the reading off the sensor. And so what this means is that, of course, we decrease our dynamic range by some small amount every time we increase our ISO, because dynamic range, of course, is this simple division between the maximum possible signal that we can read divided by the smallest possible signal that we can read. And if we, in fact, are decreasing the maximum possible signal out of our image, then we are, in fact, decreasing the dynamic range as well. Which really means that if you want to get the maximum quality out of your camera, it doesn't matter how new of a camera it is always going to be the case that the lower ISOs will have the better quality. That's just the fact of the matter, which means that you'll generally need to change your shutter speed or change your aperture to try to receive as much quality out of your camera that you possibly can. Now, this doesn't say much about future technology. I don't foresee this changing anytime soon, but I just want to put a little asterisk next to always, because there might be, in fact, some technology down the road in the far future that, in fact, changes this idea. But for now, this is, in fact, an issue. We also talked briefly about the sensor types, how there's two major types of sensors, active pixel sensors and passive pixel sensors. The major differentiator being where, in fact, the signal for that individual pixel is amplified. In active pixel sensors, it's amplified at the pixel site, and passive pixels is, in fact, amplified after it is, in fact, read. And, by the way, I have a neat another one of those neat videos showing how a CCD is made. So let's take just a couple minutes and watch some more information on this.
A CCD semiconductor is the image sensor in a digital camera or camcorder. When you snap the shutter or press record, you expose the CCD to patterns of light. It captures them electronically by converting them into millions of electrical charges. The camera's processor then reads these charges and translates them into pictures or movies. CCDs, or charge-coupled devices, are made of silicon, the main element in sand. What's special about silicon? When light hits it, you get electrons. Production begins with a round silicon wafer 6 inches in diameter and about as thick as a shirt cardboard. It goes into a steam oven for 3 to 4 hours. The intense heat, along with oxygen and hydrogen gases in the steam, create a glass-like layer on the wafer. This insulates the silicon against the miniature electrical circuitry that will be built on top of it. But first, the wafer is covered in conductive material. This layer measures less than a micron. A human hair is 100 times thicker. Next, a robot applies a 1-micron thick layer of photosensitive resin, which will undergo a chemical reaction when exposed to light. A technician places a mask over the wafer. The pattern on this mask is the schematic for part of the circuitry. When you take a picture, you expose the silicon wafer to light, and that generates electrons. The circuitry carries those electrons to the camera's processor, which reads the charges and translates them into an image. This machine exposes the masked wafer to ultraviolet light. The resin underneath the circuitry pattern remains intact, protecting the conductive layer beneath it. The resin on the areas not masked by the circuitry pattern needs to be removed. Chemicals are sprayed on. This dissolves the resin, exposing the conductive layer underneath. Technicians repeat this entire process with anywhere from 13 to 30 masks until they've built up the full circuitry pattern on the wafer. Next, technicians submerge the wafer in acid, which eats away the uncovered conductive layer. So now, the only conductive material left on the wafer is the actual circuitry. Next step, a thorough rinsing in tap water to remove the residue. Then a rinse with purified water to remove any impurities left by the tap water. Throughout production, contamination is a concern. A single speck of dust can ruin an entire wafer. To protect and insulate the circuitry, the wafer is coated in liquid glass, then baked for 2 hours until the glass hardens. The wafer surface is divided into 25 million tiny square cells called pixels. When you take a photo, each pixel records the light intensity of a minute portion of the scene, generating an electrical charge. A filter on the CCD translates each pixel charge into color. The company makes this filter with 3 pigment powders: red, green, and blue. These 3 colors combined in varying ratios can reproduce any color. The camera's processor reads and then reconstructs the photograph scene pixel by pixel. Each finished CCD undergoes a battery of automated tests to ensure that all the circuits are functional. The machine marks faulty circuits with ink. Just one bad circuit means the entire CCD needs to be discarded. Technicians then check every CCD under a microscope, looking for scratches that might have occurred during the production process. The number of pixels on a CCD varies, depending on what type of camera it's for. This one is a 25 megapixel CCD, meaning it has 25 million pixels. This company even produces a single CCD that has 111 megapixels. So the next time you say cheese, remember that you're producing a digital photo thanks to all that painstaking work that went into the sophisticated CCD semiconductor inside your camera.
So there's a few interesting takeaways from that. One of them is that all of these chips are built layer by layer on these wafers, essentially, so these circular silicon wafers that you saw. And as the size of the sensor goes up, then there's in fact more probability for problems between these layerings. So there's a variety of things at play here. One of them is the number of pixels, or the number of circuits that we actually would have in an individual CCD or CMOS sensor. The other is also the size of the sensor itself. And so they said something very interesting, where even one faulty circuit means that the entire CCD has to be thrown away. This should sort of indicate to you that as the size of the sensor goes up, there's in fact a higher probability that there will be problems with one of the individual circuits, meaning that has to in fact be thrown out, which means also as a result that the larger sensors tend to be much more expensive because they're harder to make. It's just a probabilistic thing that sort of impacts all of these issues. And what's interesting about this as well is that a lot of the technique that's shown here also applies to the CPUs that are within your computer and within your phones. It's very similar. It's the same sort of circuitry and techniques that actually go into it. However, this circuit differs just a little bit in that it actually is used to capture light and record light. And so the circuitry itself is a little bit different, but the process is somewhat similar between each of these devices. So this was a clip, of course, from that show, How It's Made. If you're on Netflix, there's, I think, just the first season, which is just like, it's just so tantalizing. You want to watch more of it, but it's also on a variety of stations here and in Canada and in the UK. And so I encourage you to watch that if you're interested to know more about a wide variety of how things are, in fact, made. Now, there was one of the things that we had in fact mentioned was the fact that there is a lot of circuitry involved in just even a single pixel for all of these sensors. And many of these sensors have millions and millions of these individual pixels. And this really alludes to some of the difficulties that manufacturers have when creating a very efficient camera, a very efficient sensor that is meant to gather as much light as possible. So there is, in fact, the photodiode. And again, I'm showing you this circuit diagram, not asking you to understand what it means, but only to look at it from the high level. And that is that this is an individual pixel for an active pixel sensor, a CMOS sensor. There's one piece of circuitry right here, the photodiode, that is actually responsible for responding to light, which varies in amount of voltage that's stored within this individual pixel. And then there's a bunch of other stuff as well. In this case, if you're curious, there are transistors that actually allow the camera to read the voltage data that comes off of that photoresistor. And so what this essentially means is that there's a lot of other stuff in an individual pixel other than just the thing that is able to capture the light, which means that if we have a huge percentage of the sensor that's not actually responsive to light, then this is a huge opportunity that's lost. And so we showed this diagram that attempts to describe how we are fixing this issue by having a small lens called a micro lens on top of every individual pixel site to focus the light that falls on top of that site onto the photodiode, onto the thing that actually captures and records that light, allowing the remainder of the pixel, the circuitry, to not actually impact the quality of that light that's being recorded. But I also mentioned something that was somewhat sensational in that cameras can't actually understand color necessarily or inherently. And the reason for this is that the photodiode cannot actually interpret color light. It only can interpret the quantity of light, the intensity of the light that has hit it. And so this was alluded to in the How It's Made video just briefly, how there's a mask that sits on top of it, a color mask, a color filter that actually allows only certain frequencies of light to fall on top of a certain pixel. And there were 3 of these colors, of course, the red, the green, and the blue, which is very similar to the colors that we use to make up an image and display it on a computer. But there's somewhat of a problem because these pixels are arranged in a grid-like pattern with a square pattern with 4 adjacent pixels next to one, so on. And so how are we actually going to decide how to do this? And this was how to actually align all of these filters so that we can accurately represent all of the colors that we want. So I teased this for just a little bit, and I want to continue doing that for just one more second as I explain something else about this. Older cameras, and I don't even mean necessarily that old, but even compact cameras and digital SLRs that are just a couple of years old have focused their efforts on improving micro lenses specifically for a frequency of light that is meant to be most important. And so if you go back and recall our discussion in the histogram lecture about luminosity, we were saying that in terms of human vision, there are some colors that are more important than others when detecting the apparent brightness of light. So that was what? What color was that? That was most important for our vision? Green, right, exactly. So, and last week there was a very good point that was brought up in that the micro lens might actually, in a similar way to a prism that sort of splits the light into its component colors, a micro lens might in fact do that in some small way and only allow certain colors to fall onto the pixel. And so this was proposed as a way of actually solving this problem of overcoming the issue of detecting color. And while that's a great idea, that's not what is actually happening here. But what is in fact happening is that this lens that in fact focuses the light is optimized for green wavelengths, to try to focus green wavelengths into the pixel below. And what this means is that it's occasionally the case that other frequencies of light will be shifted just slightly. So very much like if you sort of imagine a prism where light falls upon it and then it splits that light into several different color components that actually fall within like a table or something like that. This very similar thing is happening in the lens and in the micro lens in particular. And if we are focusing on a particular frequency that we actually want to be focused on this photodiode, then it is in fact possible to get some smearing of light as a result. And this can actually lead to, in some cases, that purple fringing that you might see at the edge of high contrast areas. But that's not the only reason that in fact happens. And now a lot of micro lenses are improved to a degree that is not really the case out of these micro lenses, but we still see it happening, but that's usually a result of the lens. And we'll talk more about that when we talk about artifacts. But let's come back to this idea where we have various layers on a pixel, where we have a micro lens that focuses light through a color filter so that we only receive some amount of color through it, and then further focuses that light onto the photodiode that actually records and captures the photons that allow the camera to actually record the light. We have this, and of course, if we're saying that green is in fact one of the most valuable components in all of these, between these three colors, then maybe it stands to reason that we want to have more pixels that in fact record green than record red or record blue. And it just so happens, of course, that if we think back to that luminosity function, that green was about 60% and blue was about 30%, and rather red was about 30% and blue was about 10%, plus or minus some percentages there. But that really means that green is about twice as important as red. So maybe it is fine to say that we should have 2 greens for every red pixel that we have. And in fact, one of the most common array types of color filters is the Bayer filter color array, and it looks like this. You'll notice that it is arranged, of course, in a square, but the most prominent color here is green. But take a look. Essentially, this is a grid pattern repeating, a grid of 4 pixels that repeats over and over and over again. It's blue, green, green, red, and so on. And what this means is that at every individual pixel, we're not in fact receiving all of the color information for that, so we have to reconstitute the original color in some way. There must be some way that we can try to figure out the individual color that existed at this particular location. And there's some algorithms for that, but I want to talk a little bit about this color filter array, in that this, for some reason or another, is one of the most popular types of color filter arrays that exist on the market, but there are others as well. And there's a wide variety of them, in fact, and some companies attempt to use alternate color filter arrays as marketing tools to say, oh, the improvement in the color reproduction of this camera is noticeable because we're not just using red, green, green, blue like all of our competitors. We're in fact using emerald or cyan or some other exotic color like that. And I think it remains to be seen whether or not there's any improvement in having an alternate color filter array over a Bayer one. I certainly wouldn't pick a camera over some camera with an exotic color filter array for any reason, just because of that color filter array. But I think there is something to be said about the fact that people have been using the Bayer color filter array for a long time and have really optimized all of the algorithms that go into reconstituting the original color. That's definitely some non-trivial aspect to this. And in fact, that algorithm is generically called demosaicing. And essentially what happens is that it considers the middle point between 4 neighboring pixels, and it tries to reconstitute color at each of those points. So we have here on the left in a sensor that has 16 pixels, 4 pixels across and 4 pixels high. And we're going to try to reconstitute each of the pixels that are, in fact, all of the colors that, in fact, made up the original image. So perhaps we could say that one of the best things that we could do is to get the middle point here between this first grid. We could get this middle point here between this second grid, a grid of 2 by 2 pixels, and then get a third pixel and a fourth pixel. But we can do a little bit better than that as well, because if you notice, if you shift over 1, we have exactly the same pattern here. It's just twisted by some number of degrees, and so we can in fact reconstitute that as well and get back a number of the pixels that made up this image. So in this case, even though we have 16 pixels, we cannot receive 16 pixels worth of color information out of this sensor. We can really only receive 1 at the very upper left, 2 upper right, 3, 4, and then the middle ones, 5, 6, 7, 8, and then 9 pixels. So sort of the numbered aspect here. That's how we could reconstitute all of these, or this is one of the ways that we could reconstitute these primary colors back into the original color that made up these pixels. Now this actually has an important implication. What this means is that there are an actual number of pixels in a sensor, but you cannot get that number of pixels out of that sensor, not at least in the original color that you had intended. There is some loss as a result of these edges not having neighboring red and green pixels to figure out what these pixels are at the edges. So there are an actual number of pixels in a sensor, and then there's an effective number of pixels. So after we run this demosaicing algorithm, we get out of it a 9-pixel image. So we could say that effectively this sensor has 9 pixels of resolution, whereas actually this sensor is supposed to have 16 pixels of resolution. And this was particularly important to marketing about 10 or 15 years ago, and especially in the early digital cameras. They would very clearly mark the actual number of pixels that a camera had and the effective number of pixels that it had, because the cameras just didn't have very many pixels to begin with. But nowadays, when we're talking about the cameras that have numbers of megapixels, it doesn't matter quite so much. We're just losing rows of pixels along the edges of the image, and we certainly have enough pixels otherwise to really have a complete image. But still, we're not getting back all of the data that we should out of this sensor. And this is sort of an interesting problem that we have. There's issues of resolution where we have we effectively have a much smaller resolution sensor than we would have otherwise. If every single pixel could detect the red, the green, and the blue components, or could just detect the raw amount of color, it would actually solve a wide variety of issues. So imagine for just a moment that I have this sensor, it's somewhere in a camera, and I have a lens that's pointed at a brick wall, for example. And a brick wall happens to have red bricks followed by white mortar, followed by red bricks, followed by white mortar, so on and so forth. It has a changing pattern. It has red followed by white, followed by red, followed by white. And we could say that this pattern has a frequency to it. If we were to step farther away from that wall, it would appear as though that change happens more quickly. If we step closer to it, it seems as though that change happens less frequently because it looks like the apparent size of the bricks are bigger. But imagine for just a moment that I have that pattern focused on this sensor, and I'm trying to figure out what color information there is at each individual pixel. So imagine that this column sees all of the red pixels. Imagine that this column sees all of the white mortar. Imagine that this column sees all of the red from the red bricks, and this column sees the white. Now, if we were using some sort of algorithm to try to figure out what color actually exists between these two pixels, you can imagine that there might be some issues with this. In fact, this is precisely one of the issues that occurs because of this style, because of this color filter array. And it doesn't matter that it's Bayer versus some other exotic color filter array. If we have some pattern that repeats, some high contrast pattern, you can think of it even more simply as just lines of black and white. Or imagine the pattern of jeans, for example, where if you were to look at the denim pattern, it sort of alternates blue and white threads in sort of typical jeans, especially if you look at the inside of it. Then you can have this very high frequency change from blue to white to blue to white. And trying to reconstitute that color is going to confuse this algorithm. It doesn't matter to us what this algorithm actually does. What the main takeaway is that it has to use 4 neighboring pixels to try to essentially not average them, but to figure out exactly what that color is going to be. And if that color changes from one pixel to the next, then it's going to confuse this algorithm, and it's not going to give us the correct color that we were expecting. So is there a way that we can fix this? Well, there is. In the electronics realm, we would call this a problem with high frequency changes. So the high frequency being that there's a change from black to white to black to white, or blue to white to blue to white very quickly. And so we would want to eliminate this with something called a low-pass filter. And a low-pass filter is precisely another object that is on top of your sensor. So we have this set of layers that make up a sensor. We have the electronics itself. We have the well that actually involves all of the electronics, and then the photodiode at the bottom of the well, and then we have the color filter array on top of that, and then we have the micro lens that's on top of the color filter array. And the micro lens is not just one lens, it's an array of millions of lenses on top of every single one of your pixels. And then on top of that, we have this other thing called a low-pass filter. Another way to think of it, or another way another thing that it's called, is an anti-alias filter. But essentially, all that we care about and all that it really is basically a blur filter. It basically blurs out all of these high-frequency issues. So there is actually, in your digital camera right now, an optical device that is meant to make it a little bit blurrier, that is meant to make the scene a little bit blurrier than it just actually is. And this is to try to smooth out these issues so that rather than have black, white, on this sensor, it would try to smooth it out to be like gray, for example. And this happens at a very fine level. Obviously, it doesn't eliminate all of the detail in your sensor, because then you wouldn't see a scene at all. It just removes these very, very high frequency changes in color to try to eliminate this problem of how do I reconstitute these individual colors back into its original color if I don't actually know which color is which. There's no context for that. This actually results in a lot of problems that we'll see, especially in the artifacts lecture in just a few weeks. But this is, in fact, one of the issues of digital cameras today. Is that because the photodiodes can't understand color, we have to have this color filter array on top of them. And as a result of that, we have to have an algorithm that is then able to recombine neighboring colors to figure out what the original color in the scene was. And because we have to use multiple pixels, if we have some pattern that actually falls on individual pixels, and it changes so frequently enough that it in fact changes from one pixel to the next, and the algorithm will get confused. So as a result of that, we have to put an anti-alias or a low-pass filter on top of it. It's getting pretty complicated to make one of our sensors. Now, there is a sensor technology that gets rid of a lot of these issues. The Foveon sensor is actually a really neat way of trying to get rid of these issues by not allowing the problem to begin with. So in this particular case, it uses properties of silicon, and in fact, the way that silicon actually absorbs color frequencies as light shines through its depths, to try to figure out precisely at every individual pixel what the color is at that one pixel location. So imagine that we are looking at a sensor from the side. So this is an individual pixel, but we're looking at it from the side, and it's made out of silicon that has certain depth. And this is this is still measured in microns. This is very, very small amount of depth. But what happens in silicon is that the higher energy, or the frequencies with higher energy tend to go further into the silicon than the frequencies with lower energy. So that means that we can put photodiodes at different depths in the silicon to try to capture some of the frequencies of light. So at the very bottom, we would have red absorption. We would have a photodiode for red. Above that, we would have a photodiode for green. And above that, we would have a photodiode for blue. And then we would know precisely the value of the red, the green, and the blue components at that individual pixel site. And this seems great because now we can actually recover all of that detail information. We can throw away this low-pass filter, this anti-alias filter, and receive the full complement of detail out of this sensor. But there's an issue with this, and the issue is that it's very difficult to tease apart what color is actually blue, because notice that at the very top level, not only are we recording blue, but we're also recording all of the red information and all of the green information as well, because that has not been absorbed by the silicon yet. So there still has to be some mathematical trickery to try to figure out precisely what the value of blue should be, precisely what the value of green should be from this entire clump of silicon and photodiodes. So what this means is that Foveon does give us back this loss in resolution that we have because of our demosaicing algorithm and in particular our low pass filter, but in exchange we lose the clarity in the color. So we get a lot more color noise, especially in the blue channel, because it's a lot more difficult to try to figure out what that value should actually be. One of the other advantages of this, however, is that we can then have pixels that are much larger, therefore capture much more light at individual pixels, and because it is much sharper, this loss of resolution doesn't really matter. Now, let me show you an example of this. Here are a few images taken with different types of sensors. There's two types of sensors, a standard Bayer color filter array sensor and also a Foveon sensor. Let me zoom in on some of these. So we have here on the left, we have a photo taken with an original 5D, and we can sort of see the way that these look. I think this is something from a flower. We can actually see these diagonal lines that emanate from this, and pay in particular close attention to the edges between this thing on the flower and the background. We can actually see the appearance of that edge. But if we take a look at a sigma, or rather a Foveon picture, even though it has this lower resolution, let's then blow it up to be approximately the same size as this 5D. Notice that in fact looks a lot sharper. And the reason for that is that there's not any guessing going on about what the color should be at every individual pixel. So imagine if we have an array of pixels like this. And imagine that it is in that same color filter array as shown before, the blue, green, green, red sort of situation. Imagine that we have a line that's projected onto this sensor. And the line is not in fact vertical or horizontal. It is in fact diagonal. So that means that this might be illuminated black, and this will be illuminated black, and this will be illuminated black, so on and so forth. Something like this. What this means is that when we reconstitute this pixel, and when we reconstitute this pixel and this one, it's not going to be able to recombine this information into a perfectly diagonal line. There's going to be some guessing that's going on, and so what we see as a result is some artifact that makes the line appear slightly more jagged than it really should. This is just the result of this issue of having to take 4 pixels and condense them down into one color, and realizing that this pattern is not going to fall very evenly across this series of 4 pixels. So even though in the raw pixel count, the sigma has a smaller count, then I keep using the word sigma because sigma cameras tend to use the Foveon type of sensor. And so I tend to use the two interchangeably, but I am talking specifically about Foveon style sensors, but in this case it's being used in a sigma camera. So that's why I keep using that particular word. But compare this now again to the sharpness in the sigma or in the Foveon image. And there's another example as well, especially any example that has very high frequency changes. Again, frequency in this case is the idea of how quickly a pattern will change on the sensor itself. Very high frequency means that it changes very, very quickly. We can see that we can really get some additional detail out of individual pixels that just end up being blurred away because of the low-pass filter. The low-pass filter removes these very high frequency patterns in the scene, and as a result, it does in fact cause a little bit of blurring within our image. But like I said, this doesn't mean that these Bayer type sensors are all bad. It does, in fact, there are, just like anything, compromises to this. I sort of wish that we see more development in Foveon sensors. I think that if we were to have more Foveon cameras that were in fact popular and people tended to use them, then we would get a lot more development out of them. But the Bayer color filter array has had a lot of development time behind it from a wide variety of major camera manufacturers, and really the Foveon type sensors we can only find in Sigma cameras for the time being. But again, it does have this issue. Even though we have this increase in resolution, it does have this problem with chromatic errors or color errors in the in the image. Particularly the noise looks pretty poor, and especially in the blue channel does it look especially bad. Now here's another example of what the low-pass filter actually does to an image. Again, it removes the high frequencies. If we didn't have the low-pass filter, so we have here 3 images. On the very far left is the original image. And notice that in this case, this is, I think, a shoe, and it's like a folded over piece of denim, that same analogy that I mentioned before. Notice that the pattern that we see in the denim does in fact seem to change at individual pixels. It's blue in one pixel and white at the next one, blue in one pixel and white in the next one. If we were to actually use a Bayer color filter sensor with this image and did not have this low pass filter, what we would get is this image in the middle. Now largely it looks the same, but notice in particular what happens to these high frequency areas is that we get strange banding of color because it's guessing as to what color is actually at each individual pixel. And we also get this sort of maze-like appearance of the color. And this is, in fact, is precisely the issue that we would see if we didn't have the low-pass filter. But what the low-pass filter does do is eliminate that detail entirely. So we get this image on the far right, where we don't have those issues with the color. We don't have those issues with this maze pattern that actually appears in the image, but now we've lost that detail. So in the grand scheme of things, this is perhaps better because this would be horrendously distracting and very difficult to remove in each of our images. But of course, we then lose that detail that used to be there in that image. Any questions on this? Yeah?
You notice the recent fashion trend in sensor design where they use a more complex pattern and then remove the low-pass filter. And there's a lot of companies doing like, they don't use the anti-aliasing filter, but they use a more complex pattern that's less susceptible to the water.
Well, I think any pattern will suffer from this to some degree. Perhaps there is patterns that reduce the likelihood of it happening in types of photographs that are, so maybe in certain styles of photographs you're less likely to see certain patterns of frequencies, and so they could arrange the color filter array to try to eliminate those issues, at least in the most common case. But you will have problems with this in those cases where you have a high frequency change in the color that is not captured well by this color filter array. So I think there are a variety. So Sony in particular has experimented with a lot of different color filter arrays. They're the ones that have had emerald and yellow and cyan and all sorts of stuff, and not really seen necessarily any benefit to those. Perhaps some of those colors did shine through a little bit brighter, but there were other issues that didn't make them necessarily the best choice. But I think we do see, especially in scientific realms or in astrophotography, where it's better to remove this filter and then be able to reconstitute that image on your own later, when you actually have the ability to perform this demosaicing algorithm on yourself and actually try to capture these images or try to capture these differences manually. Perhaps we would see that, but I think for the vast majority of us that just want to take photos, it's necessary to continue having the anti-alias filter on top of the sensor to eliminate these problems. Are you referring to a specific camera though when you mention exotic ones?
A lot of the modern cameras coming from Nikon
Yeah.
don't have an anti-aliasing filter. Fuji's new line doesn't have an anti-aliasing filter.
Right, so I think
Different pixel size pattern, so not necessarily different colors that they're trying to pick up, but a more complex pattern in how the colored pixels are laid out, so they're less susceptible to repetitive patterns.
right. So I think so correct me if I'm wrong, I think the Nikon ones are meant for astrophotography. I think they're meant to capture more detail in that way, and there's limitations to that, but I think it does also provide a benefit to astrophotography where the low-pass filter would just eliminate some of the details in the sky that you would want.
Their resolution
Right, right. So just to repeat for the folks at home, some of these sensors are so high resolution that we're in fact seeing limits against the resolution of the lens itself, which means that the lens is essentially acting as a little bit of a low-pass filter. And we do actually see that we hit the resolution of lenses even with the low-pass filters on some of these very high megapixel cameras. Even now, as technology progresses, we're finding that we're reaching a point with many lenses that we have to improve our lenses just to get better resolution out of them. And that's one of the major differentiators between the very expensive lenses and the less expensive lenses is the resolving power of those, the resolution that's capable of those lenses actually providing to the sensor. Generally, you need the higher quality lenses to actually get the full amount of resolution out of your sensor. But that's really only true if you have an extremely high resolution sensor, I would say. Okay, so this is essentially the combination of things that make up your sensor. When you actually open if you have an SLR, if you've ever enabled the cleaning mode, which folds up the lens and moves the shutter out of the way, you can actually see the sensor itself. What you're seeing is not the pixel, but you are in fact seeing at the very top layer is the low pass filter. And then below that, you're seeing, I mean, you can't really see them with your own eyes, but you're seeing then the micro lenses on top of that and so on. And so you're not really seeing, you're several layers away from the actual electronics itself, but still I wouldn't necessarily recommend using any liquids on that topmost layer because it's likely that it could go around the sides and then still go through to the sensor underneath. But let's take a step back and start considering these sensors a little bit more holistically. So now that we know that we have these sensors that are made up of all of these pixels and each pixel has a variety of layers associated with it, we've talked at length about the idea of dynamic range. And I think I mentioned this before, but really we can think of contrast as sort of a way of changing the dynamic range for a particular scene. So I have here a photograph with a histogram, and we can see that the photograph has some appearance to it, and we can see the histogram. This histogram, by the way, is an RGB histogram, not a luminance histogram, so that we are seeing the actual values, the summed values of the red, the green, and the blue color channels, and displayed on this one histogram. And we can see that there are basically no values of color below about 25% and above about 75%. So essentially what we see is we see some tones that are only contained within approximately the middle 50% of the tonal range of this image, or of this camera more specifically. So one way that we could describe this scene is that the dynamic range of the camera actually exceeded the dynamic range of the scene. So we could try to increase the dynamic range of the scene in this case by actually increasing the contrast some degree. So by doing this, we've now expanded all of these values out to their perhaps original values. We are in fact getting blacker blacks and whiter whites. All of these values are now spread out a little bit more. In fact, if you play with a contrast slider in your image editing application, what you'll see is that is in fact precisely what the histogram is doing. Is it is either compressing as you lower the contrast, or it is expanding as you increase it. Now in this case, we could argue that we've increased the contrast perhaps a little bit too much. There are values that appear to be very, that have essentially gone to 0, and there's some values that have gone to 255, which means that we're perhaps blowing something out. But we could take it, in fact, a step further and increase the contrast even more and receive this image. So this, of course, is an even more contrasty image. But notice what's happened to the histogram. This is kind of an interesting thing. We have now a lot of values that are totally 0 and a lot of values that are totally white, or at least because this is an RGB histogram, it's not necessarily white, but we have some values that are full on 255. In this case, we've probably clipped some color information in addition to probably having some white pixels that are overexposed as well. But notice that we now have gaps between some of these values. This, in fact, is something called posterization. We can see it much more easily in the histogram than we can in the image. But if we could see this in the image, what we would actually see is that gradients of colors would actually no longer appear smooth, but they would appear to have steps to them. So a dark blue, for example, just as an example, a dark blue would become light blue by steps rather than by a smooth gradation, by a smooth change in the color information. And this is the risk of modifying your images when you're using a JPEG file. There's only so much information that's contained within one of these JPEG files, and as you manipulate it, and especially if your image needs a lot of manipulation, in this case I would argue that this is way too much contrast for this particular image, but that's of course a subjective thing. Your image, especially if you take it through, I don't know, an airplane window, for example, or if you're taking it through a car window, any additional glass that you put between you and the scene that you're actually trying to capture will decrease the contrast a significant amount. And if you then go back and try to increase that contrast, you could in fact receive some posterization as a result. So conceptually, what's happening here? How are we getting this posterization? How are we getting these gaps in this histogram? Well, recall that if we have a JPEG image that is made up of 8 bits of color information, which means 256 discrete values of red and of green and of blue at every single pixel site, as we increase the gap between each of these, at some point there is going to have to be some spacing that happens as we actually try to stretch these values apart from each other. Because we don't have any intermediate values that are contained within, and so we cannot, in fact, make a smooth histogram out of this. Now, does this really matter? I would say that it's pretty difficult to get posterization in practice. You have to do some really major modifications, even to a JPEG file, to get some significant posterization like you would see here. I made a rather large contrast change that I wouldn't normally make. And even so, it's kind of difficult to see evidence of posterization. It just appears as though this image is very, very contrasty. But it is definitely possible, and it's something to watch out for. And if you're trying to create an image at the highest quality possible, then you really want to watch out for this. All right, let's take a quick 5-minute break, and when we come back, we'll continue talking about dynamic range and sensors. So before the break, we were talking about dynamic range and how contrast is related to this. And so really the takeaway from this is that we can sort of compare we can try to manipulate the contrasts of an image to try to fit the dynamic range of the scene into the dynamic range that's possible from the file that we are producing. And so what this effectively means is that generally, if you receive an image where the scene has a very low amount of contrast because you're taking it through another piece of glass, for example, or if the scene just so happens to not have very high dynamic range, one of the things you might want to do is to, in fact, increase the contrast, but of course to be careful, because doing too large of a manipulation will in fact cause issues with the data itself, like posterization. And just to hammer this idea home, I have an example here with an actual image that I took many years ago. This is a sunset image which in New Mexico near Carlsbad National Park, and it is, I don't know, it is what it is. And I wanted to, in fact, increase the contrast a little bit. I really want to try to get a little bit more contrast out of this image, and it's important to realize the distinction between contrast and saturation. Saturation would give me a little bit more color, but in this case I'm just arbitrarily going to increase the contrast of this image. Now I have created an adjustment layer in Photoshop like we had talked about in the past so that I can make these edits non-destructively. And I've also checked, because I have a relatively new version of Photoshop, I've also checked this box that says Use Legacy. And Use Legacy means that Photoshop will allow me to modify the contrast in the standard way that I would expect. If you have this unchecked, if you are not using a legacy contrast in the latest versions of Photoshop, it's going to try to prevent you from editing or modifying the contrast to such a degree that you are clipping color information. So it will actually do some mathematical trickery to increase the contrast, but really only expand the middle tones and allow them to go against the edges, but not go over, not go beyond. But in this case, I actually want to see what happens when I do a regular, normal contrast enhancement to this particular image. So right now I have a contrast of 0. I'm going to increase it a little bit. Notice that it does seem to be increasing the contrast between some of these areas. But notice what happens in particular to the blue sky as I increase the contrast more and more and more. No longer do I have this very smooth gradient from the sun to the dark sky, but in fact I am getting this issue of posterization. And this is as clear of an issue of posterization as I can make, is that we have, whereas before we had a very smooth gradient from the sunset through the blue hues all the way up to the black part of the sky, we now have this posterization where we only see chunks of color. And normally what you have to look out for is something much more subtle. You're normally not going to take your contrast slider to this degree, but in fact doing small modifications to it, even to this degree, we have introduced some level of posterization to our image. So watch out for that is really the main takeaway from this, and be careful not to overdo the contrast slider in your image, because you can get issues of this even in small localized portions of your image. But especially perhaps one of the easiest ways you'll notice is if you have a gradient like this dealing with the sky, or any gradient that is an individual color. You'll very easily get issues of posterization within that image. Okay, a refresher. So we've talked about this many times. Don't forget, a bit is either a 0 or a 1. A byte is 8 bits. So that means a byte allows 256 discrete values from 0 all the way to 255. Nothing new here, just purely review. And hopefully now you're saying, OK, now I understand why at the very beginning of the class we were in fact talking about this. And that is because when we talk about this final aspect of digital cameras, in particular their sensors, this comes into play a great deal. So imagine we have individual pixels that have all of that circuitry and all of that stuff that allows us to record the voltage, or to record the number of photons, the photons that have fallen within a pixel, and we want to actually try to record that information. So what happens within the circuitry is that it changes a voltage from a voltage of about 0 to some high voltage, and then there's some circuitry that tries to read the voltage from that pixel and convert it to a digital number. So we call this conversion, or we call this thing in a camera that does the conversion, an analog to digital converter. Because in fact the pixel is an analog thing. It's an analog device. It has a continuous number, continuously variable voltage from 0 volts up to some amount. It may not even be 0. It may operate at some base voltage that's slightly different. But I did here a variation from 0 to 1 volt just to provide an example. This is not necessarily the voltage that your particular sensor operates in. It doesn't matter what the voltage is in your camera. But what we want to do, and by we, I mean we as the analog to digital converter, we want to try to figure out precisely what that voltage is relative to the maximum voltage and convert that into a binary number so that we can then record that information in our file. This is sort of one of the last steps that actually happens in the digital camera before we have some digital output that's then saved, to the memory card on your camera. So we have here an analog sensor. It has a voltage because some photons have fallen within this photodiode, and the voltage is increased to a value of 0.55 volts. And then we need to do some sampling. And what this is we are essentially breaking down all of the individual, or this continuous variation in voltage here, to some binary representation of that voltage. And what this means is that this can be approximate. It's not necessarily the case that the value, the binary value that represents this voltage is in fact the most accurate representation of that voltage. there's some error that's happening here, some rounding error. And at the most extreme, we can think of it as posterization, where we're taking some, if we only had a couple of bits of information to take this sensor and convert it into a digital output, let's say we only had 4 bits of information or 2 bits of information, what this essentially means is that our nice looking gradient is essentially going to become posterized because we can either accept black or white or maybe 2 values of blue. So this is the most extreme version of it. And one of the other reasons why we're talking about posterization is that if we have an analog to digital converter, we have to have an appropriate amount of digital resolution to appropriately capture the voltage in that sensor. So analog to digital converters are measured in bits, or how many bits is possible, are those converters capable of outputting in resolution at that individual site. A 1-bit digital converter would be pretty much useless. It would either be off or on, which means that we would either be able to record the fact that some pixel is totally dark or some pixel is totally bright. That's not going to be too useful. So maybe a 2-bit analog to digital converter will be a little bit more useful. In fact, it would allow us to record 4 states, but still it's not quite there. We would see the posterization that we saw just a moment ago. So sort of the simplest version that we could have is this 8-bit sampler, this 8-bit analog to digital converter that then allows us to take values from 0 all the way to 255, take that output and actually spit it onto the memory card. Now imagine though for just a moment that the dynamic range of the sensor is actually different than the dynamic range of the digital converter. So you might be wondering, how is it possible for us to have an analog to digital converter that has a different number of dynamic range? Well, imagine that we have this 8-bit digital converter and we have a value of 1 as the minimal. There's a value of 0 obviously, but we take a value of 1, we can double that and double that and double that, and essentially what this means is that we are accurately able to capture 7 stops of dynamic range from our 8-bit digital converter. But now imagine that we have a sensor that's capable of recording far more stops than that. Maybe 10 stops, for example, like a typical digital SLR. What this would mean is that we were throwing away all of that possible data in our digital conversion because we don't have enough bits to appropriately convert a voltage into some binary output. So what actually happens is that we have a lot of data that just cannot be represented in that particular case. And so what we see is that many digital cameras have, in fact, analog to digital converters that sample at a much higher rate. Not just 8-bit, but maybe 10-bit or 12 or maybe even 14 bits of information. And again, don't forget that every additional bit that we add is a lot more than it sounds because it's doubling the amount of information. So going from 8 bits to 12 bits is not just a few more pieces of information. What we're talking about is doubling it 4 more times. So whereas before we had a value of 0 at the bottom to 255 at the top, with 12-bit sampling, we can have 4,096 possible values rather than 256. That's a lot more values that we have to work with. Which means that our sampling, our quantization error, that's just a fancy way of saying our ability to bucket this continuous analog variation into, shoehorn it basically into some individual piece of digital output, means that this error goes down an enormous amount. But this should also say something else to you, in that if our digital cameras do in fact behave this way, that we have sensors that have maybe 10 stops or more of possible dynamic range, and then we have an analog to digital converter that operates in these higher bit ranges, what's happening to all of this other data? How is this in fact being stored on the camera? Well, sensors are in fact linear. The way the sensors, the analog to digital converters, are in fact linear. And so what this means is that we have one stop of information is devoted to twice as much additional information. So recall that one stop change in the number of photons results in a doubling or halving in the amount of brightness. And that, in the fact that sensors are linear, means that the files that come out also behave the same way. Essentially, that means that at the very bottom stops, we have one stop of information from the value 1 to 2, and then another stop of information from the value 2 to 4. So there's not a lot of information in these lower stops. But as we keep going higher and higher and higher, we're allowing more values to represent the possible changes in the amount of photons that actually exist. And this, again, is because of this doubling and halving of the amount of light. As we double the light more and more and more, there's a wider range of photons that actually exist in the world before we have to get to the next stop. So this means that really the top half of all of the data that's coming out of our camera is devoted to a single stop of information. The next half has half that information, but still, in this case, is quite a lot. We still have 1,024 different values that can, in fact, represent one stop of information, and so on, and so on, and so on, and so on. Now, if you were to actually look at a file that stored stop information in this way, it would be totally unusable. It would be completely dark because all of our information would be in the lower stops. Remember that it's the camera is trying to expose for the middle exposure for that sensor, which means that all of the data is kind of pushed way to the left, way down in the lower stops. Which means that if we were to open this up, it would look really, really dark. But fortunately, there's a tone curve that's applied to this to try to compress this linear information into something that is much more pleasing for us, something that actually maps the way that we look at things in the world today. And by that, we get rid of a lot of this lower output. So these first few stops of information where there's really not enough value to have any difference between the representative photons, the representative brightness in these lower stops. We throw all of that information out. Likewise, we throw away some of the highest values because really this upper half is really devoted to a single stop of information. But what we want are these middle values, that are somewhat down here, but we're going to try to represent them in our file in the middle representations of these values. So we're essentially going to apply this tone curve. So what does this tone curve do in words? Well, it really compresses the highlights and the shadows, and it extends these middle tones. And we talked about this tone curve just a little bit before, but this really is meant to approximate what we see. Sensors operate in this linear fashion where it applies individual stops to increasing amounts of values because of this analog to digital converter providing to us a certain number of bits, and the sensor is actually responding linearly to all of the photons that it captures. But we don't see things that way. We focus on these sort of middle tones and look at the exposure of a scene as a whole. And so we have to get rid of these bottommost shadows and these topmost highlights and try to expand these midtones to approximate what we can actually see. Now, what this means in effect is that we are shoehorning 4,096 values into 255 possible values, which is not a lot of information, relatively speaking. But as you've seen, 255 is certainly enough when we're talking about 8 bits of color information. It seems to provide enough information to our eyes. But this really alludes to the fact that the camera is capturing far more information than we are necessarily using in the JPEG format. And in fact, that is one of the primary differences between RAW and JPEG. These last few minutes have really been sort of the really championing the idea of using raw images because you can greatly reduce the chance of posterization because you have a lot more data to work with. The tone curve is not, in fact, applied to the raw file yet, and so you can apply a different tone curve to really change the appearance of your image. White balance is not quite set, and we'll talk more about what precisely white balance is, but it is set in JPEG. Compression tends to be lossless in the raw image and is lossy in the JPEG image. I say tends to be because there's just a couple of examples of lossy raw files trying to make the raw images in fact smaller, but the vast majority of cameras are in fact use a lossless compression. Raw files are specific because of all of the circuitry changes and all of the different types of analog to digital converters that a camera might have. The raw file is in fact specific to not only that manufacturer, but also that particular model. So sometimes the raw file can change from one camera model to the next, which means it's non-standard. And so the word portability here is really like a computer science word, meaning, can I take this file and move it somewhere else and still be able to read it? With RAW, you need special software to be able to interpret this information and to be able to display it on your screen. JPEG is so common that it's very portable and that it's very easy to, in fact, move this image from one computer to the next and from one device to the next and still be able to see it. So in terms of archival, it's sort of an interesting issue here because when we want to archive an image, we want to archive as much of the original data as we possibly can, which sort of says that, well, RAW is a good candidate for this. But because this RAW file is non-standard, it really brings into question whether computers of the future will be able to read and understand this file. It seems likely that computers will continue to read and understand JPEG for many years to come because it's such a prevalent file type that's out there. So there is this Adobe has been working on a raw file type called the digital negative, the DNG file, for a number of years now, and they try to overcome this issue by making raw files a standard, well-known file type. This may be a better way to archive your photos for the long term. However, there are some downsides to that. Because these raw files tend to be non-standard, camera manufacturers can include even more information within it that cannot necessarily be fit within the digital negative, but it's another option for you to explore if you're interested in this. Post-processing is in fact required for RAW because you have to take all of this data, this huge bit depth of 10, 12, or 14 bits of information, shoehorn it down to a portable file like a JPEG in order to send it around reasonably to your friends and to your family. But sensor linearity, and again, if you don't forget that all of these slides are, of course, online, and so if you didn't get a chance to write down all of the information here, then you can, in fact, download the PDF online. But the fact that we have this linear sensor means that the vast majority of the values that represent our image are in the upper stops of what is capable of being stored by our sensor. So as you get closer and closer and closer to actually overexposing an image, you're actually recording more data for that scene. So one of the common sayings that you will see online is this idea of exposing to the right, because you'll have the vast majority, the bulk of your information will be in these lower stops, the middle stops that actually represent the middle gray of your sensor. But when we're actually recording this in the file, this means that these middle stops are given really small numbers of values. So this idea of exposing to the right says to increase your exposure, to try to capture as much of that smooth gradients as possible in these upper stops, and then later on go back and actually decrease the exposure to properly expose your photograph. And the idea here is that you would then have higher signal, lower noise, and that you'd have more values. You'd decrease the chance of posterization, all of these sorts of things. Frankly, I think this is kind of a difficult thing to achieve because typically in a very typical scene, unless you have very well controlled light, you are going to be at risk of overexposing some aspect of your image anyway. Even if it's not overexposing white values, you are probably close to blowing out individual color channels, especially for scenes of flowers, for example, or very highly saturated scenes. You're going to be at risk of blowing these out, and losing any information due to overexposure or due to blowing out channel information is far, far worse than having fewer values representing that data. So exposing to the right is great if you can, in fact, control the light very well, or if you can see from your histogram that there is absolutely no color information in the upper few stops of your sensor. And you can then try to increase the exposure compensation from your camera just maybe a stop or two. Really depends on the scene, of course. But you can try to increase the exposure compensation to try to capture all of that color information in as much value as possible, and then later go back and actually manipulate your image so that you can get the proper exposure. Now, this is a very interesting idea, but again, I find this harder to do in practice, and so you may also find that it's not necessarily worth it, but this is what is happening when we are talking about sensor linearity, is that these upper stops get the vast majority of the information, and the lower ones get fewer values as a result of this doubling in the number of photons that corresponds to a double in the value itself for the image. And that's about it for digital cameras. But we do have a couple of really great critiques for today. In fact, we want to get through at least 2, and we might have 3. But some of these are pretty unique compared to what we've had in the past. And I say that because we have our first, in fact, fully online critique that is happening, a video was provided to me, and we'll actually be able to show that. So let me just get this one ready. Let's see. OK. So this is Chris, and he's going to describe to us his photo. I actually don't know if I should show the photo first or allow him to describe it first, but perhaps I'll try allowing him to describe it first, and then we will see the photo in just a moment.
Hi everyone, I'm Chris, and I'm joining you from Beijing. I'm sending in a photo for critique that is from a trip I took recently out to Mongolia. And this is a landscape and a portrait, and I figured that's the kind of photography that I'll be doing during this course and beyond. I like working with places and with people, so I want to practice that a lot more. This is shot with the Canon 70D. I was using an 18-135 lens, so this was at the full length of 135, zoomed in, and I was using aperture priority at 5.6. So the shutter speed there was 1/320. I was interested in trying to capture the person and the place and get a feel for the setting. You can see that the light is really quite saturated there. It was very dry, very bright light. The color palette's pretty limited with browns and yellows, but I still wanted to try to get a crispness of what it was like to be in that forest in the fall. So I'm curious to know what you think about the color, about the composition, and also the cropping. I wasn't quite sure with the subject whether to keep it as is, so you get the fuller picture, or to bring it in a little tighter. I did try to position him so that you got a little bit of sense of both, but I'd love to know what your thoughts are. Thanks very much.
All right, so do we have any comments for Chris with his photo here? Let's see, I'll try to make this full screen so we can now focus on the photo itself. John, would you mind emceeing this? Do you have any comments to start out, maybe? Not to put you on the spot, but...
No. Let's see. I like it a lot. I like the background the most, actually. I think it does a good job of capturing the person. My only complaint is that the person looks a little bit staged. He kind of looks like, oh, he's going to take my photo. I guess I'll stand here and smile for a minute. You know, and that's the curse of a photographer, really, is it's really hard to get a natural-looking picture of someone. And so I think the photo suffers from that just a little bit. I also would like to see the original before it was cropped. He mentioned having a tough time with the crop. And, you know, if I could maybe keep, how do I put this? It sort of feels like he's a little too far to the right of the frame. I feel like if we could just move him, you know, to the left third, it would feel more natural for me. But I'm also a one-trick pony and only have the rule of thirds at my disposal. So, that said, I love the light. I love the wide dynamic range in the photo, and the autumn background. You could tell me this was Concord or Cambridge, and I wouldn't have known that it was not. Somebody else, please save me from this.
Actually, while you're doing that, I want to respond to a couple of those comments. One of them is that you think he's too far to the right. It's actually pretty interesting because I was going to disagree with you at first, but I think actually that you might be right. I think one way that we could, one possible improvement to this could be that because the man is wearing a somewhat dark jacket against a somewhat darkened background, perhaps if he were moved over here where there's a little bit lighter of a background, that would kind of increase the contrast just a little bit between the background and between him, and that might, that would certainly change the character of the photo. Whether or not that would be an improvement, I'm not sure, because perhaps it is the case also that where he is now, the background is actually more interesting. The fact that we can see this part of the background is actually more interesting. So it really, I think, depends on what was behind him at the moment. So, I'm sorry, please do.
Actually, I was going to mention the same thing you just did, Dan, where I do, just because his coat is so similar to the background, I do wish he was maybe on the more brighter end. And he also mentioned how I thought about the cropping. And I do feel like the photo is a little bit too zoomed in. Just because the coloring of his clothing is so similar to the background, I do wish we could see the original of how he looked uncropped. Maybe we'll get a different perspective. But I do like the colors, and I think the focus looks great. So.
Sorry to steal your comment then.
No, I think that is a good point, Silky. And if he hadn't talked about the crop in the video, I might not have noticed this, but I really miss his feet. It's
yeah.
That's the thing. That's what makes me unsure. Now, if you're watching out there, I just want to reemphasize that I actually do like the photo. I'm just nitpicking because it's a critique.
So I really like the exposure, and as everybody said, I think if it wasn't cropped, it makes me think that what is on the side, and his shoes too. But if he would have removed the jacket, I think he's wearing red shirt inside. Mm-hmm. That would have made the photo more appealing to eye, because right now everything is camouflaging to the background. So, but I love the light, and he's wearing the sunnies, so I mean it looks very good.
Yeah, the light is phenomenal. It's interesting. I wonder if it was intentional to make the colors sort of similar, because that makes I think that actually draws attention to the man's face through the small area of the red shirt that's actually visible, because that aspect of the image has the color that pops, and the rest has a very fall, seasonal feel to it. Yeah.
Well, interesting thing is, part of me wants the actual person gone. Look, when I look at the background and the quality of the shadow and the varying light that happens, I'm more drawn to that. Mm. And it could be that the light hitting him seems harsher because you have the glare on his head, which is, as a balding man myself, I have that happen to me often. Then there's a glare on the glasses, and it's not helping. And actually the sunglasses are sort of, I want to see his eyes. There's something about when I look at a photo of a person that the eyes are really important. Mm-hmm. But now, since there is a person, I would consider bringing down the level, because it seems like right now there's a foreground and a background, but there's nothing that connects them in between, so that the bridge itself, or the fence, whatever that is really bright in comparison to the background, and he's really bright in comparison to the background. And I want a connection. I want something that moves in terms of space light-wise, so that there's a sort of, because actually if I look at this, it looks like it's a backdrop, and he put a person and a fence in front because of the difference, which is an interesting effect, but I'm not sure that's what he was going for. And if it was, he's very successful at it. So.
That's an interesting point. So it almost sounds as though, because it's this hybrid landscape, I heard two things that you preferred. It sounded to me, and maybe this is the wrong interpretation, but it sounded to me as though the hybrid attack here of having the dual portrait and landscape is not quite what you would want. You would either want the full-on landscape or the full-on portrait, is how I interpret your comments. Which means, and actually John had mentioned that just a little bit too, of being, missing his feet. And sort of my reaction to that was, well, we don't necessarily need his feet. Like, we could zoom in a little bit more on his torso. But then, of course, that's a full-blown portrait photo. And then we lose this additional context of the landscape itself. So is that kind of an accurate assessment of of your comments?
Yeah, I think because of the positioning and the difference in light, that's what I would want this image to be. However, I do think this person, if he were more in the scene than the background, it would be a completely different. Like, he would be integrated more within the landscape. And I think maybe that's part of it, is that there isn't an integration between the landscape and the portrait.
So integrating the landscape, yeah, that's a very interesting point. I think there's a couple of ways that integration can happen. One of them can be still using a long lens. This appears to be a somewhat long lens just based on the quote-unquote distance of the background, the compression of the background. Maybe compressing it even further, standing even further away, zooming in even more if possible, and really sort of collapsing the foreground into the background a little bit more is certainly one way. Another way is also to get a lot closer and then use a really wide-angle lens and trying to minimize distortion as possible. And this can be difficult to do, especially as the angle of the lens gets wider and wider and wider. But then you get more of that connection between the foreground and the background. You still have this isolating capability through this wide lens as you change your perspective of getting closer to the person and then zooming out. But you still get this isolation, but then you also, because of the wide field of view, do get more of the context of the surroundings as well. And so you can sort of envision then seeing also the ground maybe. So I do realize that we see a little bit of the ground here, but really seeing how the bridge connects to the ground, or if it is in fact a bridge or separated in some way.
We should probably wrap up this photo because we're going long. But I think a number of the issues we've addressed maybe could have been solved if the guide just tilted slightly to a different direction. So he's kind of facing this way and the sun's in his eyes. And I think that's what's making it feel a little more staged, and it's what's making the spot in his head jump out a little bit, and it's causing such an extreme difference in brightness between the subject and the background. So if the subject kind of did this, and maybe the photographer did that, it might actually have changed a lot. So I'd really be interested to see, if you're out there, student, other versions of this photo, maybe with different crops or other takes that you didn't use here. But I still really like the textures and the fall backdrop.
Yeah, I love the fall feel and the light as well. It's really very well done. Great. Well, thank you all very, very much. I apologize, Rob. We'll get to you next week to your image, but thank you very much to Chris and to Ed for providing these videos and these phenomenal shots for us to take a look at. And thank you all again. Next week, again, we will have a guest lecture with John and with Shelley, and I will return in 2 weeks to talk about color and artifacts. Until then, thank you all for coming. We'll see you then.